Welcome to the deep dive.
Great to be here.
Today we're taking a plunge into a topic that's everywhere, right? AI agents.
Absolutely. It's fundamental stuff.
We're going beyond just, the buzzwords. We want to really get into how these things think, how they learn, how they interact with the world.
Yeah, the mechanics behind the magic, so to speak.
Our sources for this deep dive, they really pull back the curtain on the, let's call them brains, of these AI systems. Everything from the super simple automated responses you see every day.
Like chatbots, maybe?
Exactly. All the way to these incredibly complex, self-improving agents that seem to, learn right in front of you.
It's a fascinating spectrum.
So our mission today, it's pretty clear. We wanted to give you a real shortcut to understanding these fundamental building blocks of AI.
Mm-hmm.
We're going to cut through the hype, get down to the surprising facts, the core mechanics that make them tick.
Get ready for some aha moments, hopefully.
Definitely. You should walk away really getting what powers everything from, say, your smart thermostat to the really cutting-edge AI that's all over the news.
And we really do mean aha moments. This dive is designed to show you, kind of step by step, how AI can go from just following basic instructions,
Like code.
right, hard-coded rules, to making pretty sophisticated decisions, even reflecting on its own mistakes and proactively learning from experience.
Reflecting on mistakes, that sounds very human.
It's getting there. It's really about demystifying the intelligence, showing you that logical progression of capabilities. We're pulling back the curtain on the how behind the what.
Okay, that sounds like an essential roadmap for anyone curious about AI. So let's start right at the beginning, laying the foundation. What are AI agents? So at its core, what is an AI agent? It's not just software, is it?
Not quite. Think of it as an entity, right? Something that perceives its environment.
Sees, hears, senses.
Exactly, through
Okay.
sensors.
Yeah.
And then acts upon that environment using actuators.
Okay, and our sources say they're classified based on how smart they are.
Precisely. Based on their intelligence, their decision-making abilities, and crucially, how they interact with their surroundings. It helps us understand their level, their tier, if you will.
And why is that classification useful? Does it tell us what they can do?
Immensely practical, yeah. Knowing the classification tells you a lot about its capabilities, but just as importantly, its limitations. It's like a blueprint for its potential.
Gotcha. And you mentioned this agent environment loop.
Right, that's the fundamental concept. Imagine this. The agent has sensors. Could be cameras, microphones, anything that gathers data. These gather precepts.
Precepts, like perceptions.
Essentially, yeah,
Ugh.
raw data, observations from the environment. Then the agent, the brain part, processes these precepts,
Thinks about it.
thinks about it based
Yeah.
on its internal logic, and finally, it uses actuators, motors, screens, speakers to perform actions back into the environment.
And that action changes things.
Exactly. It changes the environment, which leads to new precepts being gathered by the sensors, and the loop just continues, sensing, thinking, acting, over and over.
So it's a perpetual feedback loop.
Yeah.
A constant cycle.
That's it. And the sophistication of that thinking part, how it processes precepts and chooses actions, that's what really differentiates the types of agents we're about to get into.
Okay, which brings us to the big picture goal for today.
Mm-hmm.
By the end of this, you listening should have real clarity on what different AI agents can do and what they can't.
Cutting through the noise.
Exactly. Understanding the diverse functions. You'll be able to spot the difference between a simple script and a truly intelligent adaptive system. And that's getting more important every day. 2, the spectrum of agent intelligence, from simple to sophisticated.
All right, let's dive into that spectrum. It all starts somewhere pretty basic. A, the simple reflex agent, pure instincts.
Okay, let's unpack this first one, the simple reflex agent.
Yeah.
So it's basic.
It is. It's the most fundamental type. Its brain, if you can call it that, is basically just a list of pre-programmed if-then rules.
If this, then that. Super simple.
That's it. If it sees a certain condition, then it executes a specific action. Pure, unadulterated instinct, no thinking involved, really,
And the crucial thing here, the big limitation.
is memory. Or rather, the complete lack of it. It has zero memory of past events. It doesn't build any kind of internal picture of the world.
Wow. Okay, so it only knows what it's seeing right now.
Exactly. It operates solely on its current perceptions, reacting immediately. It literally can't remember what happened a second ago.
So it's like a finely tuned machine, but
Yeah.
without a memory. It just reacts. It can't learn, can't anticipate.
That's the essence of it, which makes it pretty good for stable, predictable environments. Think simple automation where the rules are fixed.
Like on an assembly line.
Perfect example. Or basic control systems. But, and this is a big but, they really struggle when things get dynamic or unpredictable.
Because they can't adapt.
Right. If a situation comes up that isn't perfectly covered by its rules, it's stuck. And because there's no memory, it's prone to repeating the same mistakes over and over. If the if condition is met, it will perform the then action even if it's clearly not working anymore.
It's like it keeps touching a hot stove because it doesn't remember getting burned.
That's a good analogy.
Yeah.
So conceptually, its brain is just that checklist. Sees something, checks the list, triggers an action. That action changes the environment, leads to a new seeing, and the cycle repeats, always stuck in the present.
Can you give us a simple everyday example?
Sure, think of a basic thermostat, the kind without any fancy scheduling. Its rule is simple. If the temperature drops below, say, 18 Celsius, then turn on the heat. If the temperature reaches 22 Celsius, then turn off the heat.
Classic if-then.
Exactly. It perfectly fits the criteria. The thermostat doesn't remember it turned the heat on 5 minutes ago or that it's been cycling all day. It just reacts to the current temperature reading.
Simple, effective for its job, but definitely limited.
Very limited. It's the foundation, but just one piece of the puzzle. B, the model-based reflex agent. Adding a memory.
Okay, so simple reflex is pure reaction, no memory. Let's level up. What happens when you add that memory? That's the model-based reflex agent.
That's right. Now things get more interesting. This agent is more advanced because, while it still uses those fundamental if-then rules...
Still reactive, then.
Still fundamentally reactive, yes, but crucially, it incorporates an internal model of the world. Think of it like a little mental map or its understanding of the current state of things.
So it's not just reacting to what's immediately visible. It's building a picture. It has some context.
Precisely. It updates this internal model, this map, by observing how the environment changes. But here's the clever part. It also understands how its own actions affect the environment.
Okay, so it connects cause and effect. If I do X, the world changes like Y.
Exactly. It learns, in a basic way, the consequences of its actions. And the big benefit. This internal model lets it infer or remember parts of the world it can't currently see.
Like knowing what's around a corner. Or where it left something?
Potentially, yes. Or even just where it has already been. So its understanding of its surroundings is much richer, even though its decisions are still based on its current understanding, which now includes that remembered state.
I see. So beyond the simple rules, it has this memory component, this internal logbook. When it acts, it updates the logbook based on what it expects to happen. Then it uses that updated memory, plus its current senses, to apply its rules. More informed decisions.
Absolutely. And what's fascinating here is that introduction of the internal model. That's where the agent starts building, a connection between its actions and their effects. It's a leap from pure reaction to a kind of rudimentary understanding.
How does that play out in an example? Maybe something more complex than a thermostat.
A robotic vacuum cleaner is a great example, a slightly smarter one anyway. Its internal model acts like a map. It knows, or believes it knows, where it's already cleaned, where obstacles are.
Like furniture legs or rugs.
Right. And it knows that moving forward changes its position on that internal map. So its rule isn't just, if sensor sees dirt, then vacuum. It's more sophisticated.
More like
it. My internal map says this area is unclean, and my sensors don't detect an obstacle right now, then move forward and vacuum.
So that internal map stops it from just randomly bumping around or cleaning the same spot over and over.
Exactly. It makes it much more efficient. It uses its memory of the world state to complete its task better. It's smarter than the simple reflex agent that would just bounce off walls indefinitely.
So the key insight for model-based agents, adding that internal model, that memory, transforms it, starts building a simple worldview, foundational for anything more complex.
Definitely a critical step up the ladder. C, goal-based AI agent. Purpose-driven.
Okay, memory makes a big difference. But reacting, even with memory, still feels, reactive. What about agents that have a real purpose, a goal? That's the goal-based AI agent, right?
That's the next major evolution. Goal-based agents build directly on those model-based ones. They have the internal model, the memory, but they add a crucial layer. Decision-making is now driven by explicit goals, desired outcomes they're actively trying to achieve.
So they're not just understanding the world, they're trying to change it in a specific way.
They have ambition.
Ambition might be a strong word, but yes, purpose. They use their internal model not just to understand the present, but to plan for the future, to strategize.
Plan. How does an AI plan? Does it imagine possibilities?
That's exactly it. It uses its internal model to simulate future outcomes of actions it could take. It plays out different scenarios in its mind.
Like, what if I turn left here versus what if I go straight?
Precisely. It simulates those actions, predicts the consequences based on its model of the world, and then evaluates how each potential outcome brings it closer to its objective.
And then it chooses the best path. It chooses the action that, based on its simulation, seems most likely to help it achieve its goal. This is the key difference. It's proactive, not just reactive. It's working towards something specific. It's problem solving.
Okay, I think I get the concept. It has a target. It uses its world understanding, its model, to imagine actions, predict consequences, and pick the one leading towards the goal. Like playing chess, thinking several moves ahead.
That's a good analogy. It's looking beyond the immediate situation. A self-driving car is a fantastic real-world example.
Right. Its goal is get to destination X.
Exactly. It's not just reacting to the car in front or the traffic light. It has its internal map, maybe real-time traffic data.
Its model.
Its model, yes, and knowledge of road rules. It might think, conceptually, okay, I'm on Main Street. If I turn left at the next intersection, that leads towards the highway. Based on current traffic and my destination X, is the highway the best route? My simulation suggests yes. Okay, plan, initiate, left turn sequence.
Wow. It's constantly running those simulations.
Constantly predicting and planning, aligning its actions with that ultimate goal. It's a massive leap in complexity, moving from simple responses to genuine strategic thinking.
So the key insight. Once an AI has a goal, it becomes a planner. It takes initiative. This is where AI starts looking truly strategic.
It's the beginning of AI driving towards objectives, not just responding to stimuli. Utility-based agent, the pursuit of happiness, optimization.
That planning ability is huge. But what if there's more than one way to reach the goal? And some ways are just
better.
faster, safer, cheaper. How does an AI choose the best way? That sounds like the utility-based agent.
That's precisely the challenge it addresses. The utility-based agent is an evolution of the goal-based one. It doesn't just care if a goal is met, but how desirable different outcomes or paths are.
Desirable. How does an AI know what's desirable?
There's something called utility. You can think of utility as a happiness score or a preference value that the agent assigns to different states of the world or different outcomes. It's like giving it an internal value system.
So it's not just achieving, it's optimizing. It has preferences, can make trade-offs.
Exactly. The huge advantage is that it can rank options. It chooses the best outcome according to its utility function, not just any outcome that satisfies the goal. It optimizes.
But that sounds tricky. How do you define best for an AI? That utility function must be crucial.
Absolutely critical. It relies entirely on having an accurate, well-defined utility function that assigns those scores. This function has to correctly capture the priorities and preferences we want the agent to have. Designing that function can be really complex, especially when there are conflicting priorities.
Okay, so conceptually, it's like the goal-based agent simulating future outcomes.
Right.
But for each outcome, it calculates a score, the utility.
Yes, reflecting how much it likes that outcome.
And then it picks the action leading to the highest score, the most desirable future.
That's the core idea. It's not just get there, it's get there in the way that maximizes my utility score, which might mean fastest, safest, most energy efficient, or some combination.
So if we connect this to the bigger picture, this is how AI moves from just doing a task to doing it well, optimizing for multiple factors, like we humans do.
Precisely. Think about an autonomous delivery drone. Its main goal, deliver the package. Easy enough for a goal-based agent.
Right.
But a utility-based drone considers more. How quickly can I deliver? How safely avoiding bad weather, obstacles? How much energy will I use? Minimize battery drain.
So it simulates different routes.
Exactly. Simulates multiple routes, estimates time, battery use, weather risk for each. Then it calculates a combined utility score for each route, weighting those factors.
And chooses the route with the highest score. Maybe one that's a bit longer but saves a lot of battery.
Or one that's faster but avoids a windy area. It makes sophisticated trade-offs based on its utility function to find the optimal overall result. It's nuanced decision-making.
Key insight. Utility lets AI make smart choices with trade-offs. Pursuing excellence, not just completion. It's AI with judgment, balancing priorities.
A crucial step towards more sophisticated human-like reasoning. E-learning agent. The student AI.
Okay, optimizing is impressive. But what if the world changes constantly, or the best way isn't known beforehand? We need AI that can adapt and improve on its own. That sounds like the learning agent, the AI that goes to school.
This is where things get really dynamic and, frankly, powerful. The learning agent is the most adaptable type because it learns from experience. It's not just relying on pre-programmed rules or fixed goals or utility functions.
It gets better over time.
Yeah.
By itself.
Yes. It improves its performance by updating its behavior based on feedback from the environment. In machine learning, especially reinforcement learning, this feedback is often called a reward or penalty. Did it do well? Get a reward. Did it mess up? Maybe get a penalty or just no reward.
Like training a dog with treats.
Sort of, yeah. It learns which actions lead to good outcomes. And it does this through a set of core components that work together like a mini learning system.
Okay, break it down for us. What are these components?
First, there's the critic. Think of it as the teacher or evaluator. It watches what the agent does, sees the outcome, and compares it as some standard of performance. Then it provides feedback.
The grade. Good job, or try again.
Basically, yeah. Often just a numerical signal, positive reward, negative reward, or 0. Then, crucially, there's the learning element. This is where the actual learning happens. It takes the feedback from the critic and uses it to update the agent's internal knowledge or strategies.
So it adjusts its approach based on the feedback.
Exactly. It modifies its rules, its model, maybe even its utility function to incorporate what it just learned. Then there's the performance element. This is the part that actually chooses the actions based on what the learning element currently thinks is the best strategy. It's the doer.
Okay, critic gives feedback, learning element updates strategy, performance element acts. Is that it?
Almost. There's one more really clever part, the problem generator. Its job is to encourage exploration.
Exploration, like trying new things.
Precisely. It suggests new actions or strategies for the agent to try, things it hasn't done before or hasn't done much. This is vital because otherwise the agent might just get stuck doing what's good enough and never discover potentially much better ways of doing things. It pushes the agent to experiment.
Wow, so it's a whole self-improvement cycle. Try something, performance, get feedback, critic, update strategy, learning, and sometimes deliberately try something new, problem generator, like a student learning through trial, error, and occasional experimentation.
That's a perfect way to put it. A great example is an AI chess bot.
Like AlphaZero or Stockfish.
Exactly. Its performance element plays millions, even billions of games. The critic just sees the result, win, lose, or draw. That's the feedback. The learning element then adjusts its internal evaluation functions, how it judges board positions, the value of pieces in context, opening strategies based on all those wins and losses.
And the problem generator.
It might occasionally force the bot to try completely new opening moves, even ones that look bad initially, just to see what happens. Maybe it discovers a brilliant new line of play no human ever considered. This continuous loop makes it incredibly strong.
So the insight here is massive. Learning agents are engines of continuous improvement. They get better on their own, often exceeding their initial programming. This is the foundation for truly autonomous, self-improving AI. AI that teaches itself.
It's the pathway to the really advanced AI we're seeing emerge now. F-quick comparison in multi-agent systems.
That progression is just incredible, from simple reactions to AI that learns and explores. Okay, before we move on, let's quickly recap the essence of each type, just the keywords.
Good idea. So, simple reflex. Reacts, fast, no memory.
Model-based reflex, remembers.
Yeah.
Tracks internal state, still reactive but smarter.
Goal-based. Aims, has objectives, plans ahead. Any way to the goal is okay.
Utility-based, evaluates, chooses the best outcome, optimizes, needs that utility function.
And learning agent. Improves. Learns from experience, adapts, can be slow to train but very powerful.
Perfect summary. And you mentioned earlier, these agents often don't work alone.
Right. Increasingly, we see multi-agent systems. This is where you have multiple agents, maybe of different types, operating in the same environment. Often, yeah. They might cooperate on a complex task, each specializing. Think of a swarm of drones mapping an area. Each drone is an agent, but they work together.
Or different AIs collaborating on research.
Exactly, combining their strengths. This collective intelligence can achieve things no single agent could. It's a huge area of research and application itself. 3, the crucial role of structure, making LLMs understandable.
Okay, we've got the brains sorted, from simple to super learner. But how do these brains, especially the really complex ones like large language models, actually talk effectively? How do they interact with other software reliably? This sounds like it needs structure.
Structure is absolutely critical. It's non-negotiable when you want LLMs to work reliably with external tools.
Tools like APIs, databases,
Yeah.
other code?
Exactly. If an LLM just outputs free-flowing text, the receiving system, the tool, has no reliable way to understand what it's supposed to do. It leads to errors, ambiguity, things breaking.
So the LLM can't just say, book a flight to London for tomorrow.
Not if you want it to actually work consistently. The booking system needs specifics. Which airport in London, what time, which airline preference, passenger name, all in a predictable format.
It needs a template, a form to fill out.
That's a perfect analogy. This predictable format is called a schema, or a data model. It's the structured order form for the LLM's output. It ensures the information is organized, complete, and machine-readable. It prevents chaos.
Like ordering a pizza, you need the size, toppings, address fields filled correctly.
Precisely. Schemas provide that structure, enabling seamless, error-free communication between the LLM and other software components. It's fundamental for building robust applications.
The blueprint for LLM outputs.
Okay, schemas are the answer. How do we create them? Our sources mention a Python library, Pydantic. Sounds like a tool for making these blueprints.
Pydantic is fantastic for this. It lets developers define these data schemas using simple Python classes. You essentially create a template for the data you expect.
And what are the big advantages?
Several key ones. First, strict type validation. You define that a temperature field must be a number, an integer or float, not text. Pydantic enforces this automatically, catching errors early.
So fewer data bugs.
Way fewer. Second, you can set default values. If the LLM doesn't provide a specific piece of optional info, a sensible default can be used. Third, and this is huge for integration, it has built-in support for JSON serialization and deserialization.
Converting the data to and from JSON, that universal format for web stuff.
Exactly. Makes it super easy for the LLM's structured output to be sent to an API or read from one. It handles the conversion smoothly.
So back to my weather example, I could build a weather schema.
Absolutely. You define a class, maybe weather schema inheriting from Pydantic's base model. Inside, you specify fields. Condition as a string, temperature as an integer, unit as a string, maybe limited to Celsius or Fahrenheit.
And then I tell the LLM to use this schema.
You bind this schema to the LLM, essentially telling it. When you provide weather information, structure it like this. So if you ask what's the weather, it feels like 25 degrees and sunny, the LLM won't just repeat that. It will try to extract the info and output a structured object. Sunny, temperature, 25 unit, Celsius, assuming it infers Celsius.
Clean, unambiguous data, ready for another system to use.
Instantly usable. No messy text parsing needed.
And it works for actions, too. The sources mention an addition tool example.
Right. Shows how an LLM can parse natural language like add 5 and 7 and structure the input for a function. You define an add input schema with fields A, integer, and B, integer. The LLM gets the request, understands it needs the add tool, extracts A5 and B7, and formats them according to the add input schema. Then a separate Python function just takes that structured input A, 5B7, and performs the addition. The LLM acts as the smart interface, translating human language to machine instructions.
Okay, so the key advantages recap. Structured output guaranteed format. Validation fewer errors. JSON handling easy integration. Reusability extends schemas for similar tools. And extensibility easy to add new tools.
You've got it. And there's another neat feature. You can restrict values even more tightly. For example, if a calculator tool only supports add, subtract, multiply, you can define the operation field to only accept those specific strings.
Preventing the LLM from hallucinating unsupported operations.
Exactly. Makes the system much more robust and predictable.
This combination, Pydantic schemas plus LLM tool binding, feels fundamental for building reliable, complex AI applications. It's like giving the LLM a proper way to interact with the digital world.
It absolutely is. It's the Rosetta Stone, as you said, allowing LLMs to reliably talk to other software. Without it, multi-tool agents would be incredibly brittle. This structured communication is what enables more complex AI behaviors, letting them reliably use tools to achieve goals.
Right, which perfectly sets us up for the next section, seeing these agents in action, 4F. Agents in action, reflection and react. Okay, foundations laid, communication structure understood. Now for the really advanced stuff. Reflection and react agents. This is where AI starts getting seriously smart, using tools and even correcting itself. Let's start with reflection. Sounds like self-reflection. Reflection agents. The self-correcting AI.
That's the core idea. Reflection agents are designed to be self-correcting. The goal is to build an agent that uses sophisticated prompting, those structured schemas we just discussed, and an iterative feedback loop to refine its own answers.
Refining how, just making them better.
Specifically with a focus on citation-backed revisions, it doesn't just fix errors. It aims to find and include evidence, like scientific citations, to support its corrected statements, like a careful researcher double-checking their work.
Wow. So it needs to access external knowledge. How does it do that?
Through tools. A key one here is something like the Tavily search tool. You can think of it as giving the AI a controlled web browser.
So it can Google things.
Effectively, yes. When it realizes it needs a fact, or needs to verify something or find evidence, it formulates a search query, sends it to Tavily, and gets back structured results, maybe the top 5 relevant web snippets. It's crucial for accessing real-time external information.
Okay, it have a search tool. How does the process start? Does it just answer neutrally?
Well, the interesting thing in the sources is how they set it up for demonstration. They deliberately give the initial LLM instance a specific, potentially biased persona using prompt engineering.
Like telling it to act like someone specific.
Exactly. The example uses Dr. Paul Saladino, known for, let's say, strong views on carnivore diets. This isn't to endorse that view, but to show the contrast. The goal is to demonstrate how the agent moves from that initial, potentially opinionated response towards an evidence-based one through the reflection process.
Ah, clever. Shows the journey from opinion to evidence. And how do schemas fit into this self-critique process?
They are absolutely essential for orchestrating it. You define specific Pydantic schemas. First, a reflection schema. This guides the LLM's self-critique, maybe with fields like missing, what info is lacking, and superfluous, what in my answer is unnecessary or wrong.
So the AI critiques itself in a structured way.
Precisely. Then there's an overarching answer question schema. This holds the actual answer field, a nested reflections field using the reflection schema, and crucially a search queries field where the agent lists the searches it thinks are needed based on its reflection.
And the LLM is forced to output in this format.
Yes, it's bound to the answer question schema. So its output isn't just text. It's a structured JSON object containing the answer draft, the self-critique, and the necessary search queries. This makes it easy for the system to automatically extract those queries and send them to the search tool.
It's like the AI fills out a self-assessment form along with its answer. Okay, how does this all fit into a workflow? Sounds like multiple steps.
It's orchestrated using a graph-based approach, often with something like LangGraph. Think of it as managing the agent's state or memory, a running list, response list in the example, that accumulates all the messages, user input, AI responses, tool outputs. This list is passed between stages.
And the stages are?
They're called nodes in the graph.
Yeah.
First, a respond node. This uses the initial LLM with the Saladino persona and answer questions schema to generate that first draft answer, the initial self-critique, and the first set of search queries.
Okay, initial attempt and request for info.
Then, an execute tools node. This node extracts the search queries from the previous step's output, actually calls the Tavily search tool, gets the results, and adds those results as a structured tool message back into the running message list. This is the info gathering step.
Got the facts. Now for the revision.
Now for the heart of it, the reviser node. This is where the reflection really happens. This node uses another LLM instance, maybe prompted with a different, more evidence-focused persona, like Dr. Peter Attia.
Shifting perspective.
Exactly. And this reviser LLM is bound to a different schema, maybe a revise answer. This schema is similar to answer question, but crucially adds a citation list field, forcing the reviser to include references.
Making it cite its sources.
Yes. It receives the whole message list, initial answer, critique, search results. It then synthesizes everything, revises the answer to be more accurate and evidence-based, incorporates the search findings, and adds those citations. Its output is a new revised A message structured by a revised answer. It might even generate new search queries if it finds more gaps.
So it takes the first draft, the critique, the search results, and produces a better cited version.
That's the goal. It synthesizes, corrects, and backs it up.
And this can loop. It can keep refining.
Yes, the graph framework manages the flow, responds execute tools reviser. But then there's a conditional edge coming out of the reviser. A function checks. Does the revised answer still need more work? For example, did it generate new search queries? If yes, loop back to execute tools. If no, or if a maximum number of loops, say 4, is reached, then end the process.
An iterative refinement loop. That's seriously cool. True reflection, seeking external validation. How did it do on a real query?
The example uses a query like, I'm pre-diabetic, need to lower blood sugar, and have heart issues. complex, multi-part.
Right.
The initial response from the Saladino persona might be very carnivore-focused, general, maybe lacking specific evidence, and likely under-addressing the hard issue aspect.
Okay, bias first draft.
But the final output from the reviser, after a couple of loops of searching and revising, is significantly better. It's more balanced, includes scientific citations, maybe mentioning studies on low-carb diets and blood sugar, suggests measurable outcomes, like tracking postprandial glucose, and provides more precise guidance.
So a definite improvement. Did it nail everything?
Interestingly, the source notes that even the improved version still didn't fully address the heart health concerns adequately, which is a really important insight. Meaning even these advanced self-correcting agents aren't perfect. For complex, nuanced problems, especially in areas like health, they might still miss things or require human oversight and refinement. It's powerful, but not infallible.
A great demonstration of both the power and the current limitations. Okay, that's reflection. Now, what about ReAct? Reasoning and action. ReAct agents. Reasoning and action in tandem.
ReAct is another fascinating approach, specifically designed for complex tasks that need step-by-step reasoning intertwined with actions.
So not just reflecting after the fact, but thinking during the process.
Exactly. It combines chain of thought reasoning, the LLM basically thinking out loud, explaining its logic step by step with the use of external tools. It doesn't just jump to an action.
What does it do first?
It reasons about what step is needed next. Then it decides which tool to use for that step. It uses the tool, gets a result, and then observes that result to figure out the next step in its reasoning.
So it's this dynamic loop, thought, action, input, observation. That observation feeds the next thought.
You've got it perfectly. It's an adaptive loop that lets the agent break down complex problems and gather information incrementally as needed.
And how does the LLM output this process? Is it structured too?
Yes, very much so.
Yeah.
The LLM is specifically prompted to output its process following a clear pattern. Thought, its internal reasoning, I need to find X first. Action, the name of the tool it decided to use, UE search tool. Action input, the specific input for that tool, e.g. weather in Tokyo. Then, after the tool runs, the system provides the observation, the result from the tool, e.g. 22 degrees sunny. This observation is fed back to the LLM for its next thought cycle. This repeats until the LLM concludes its reasoning with a final answer, the complete response to the user.
Okay, that's very clear. Let's walk through that Tokyo weather and clothing example. How would ReAct handle what's the weather in Tokyo and what should I wear?
All right. Soon we have a search tool for weather and a recommend clothing tool. User asks the question. LLM thought. Okay, two parts to this question. First, I need the weather in Tokyo. LLM action.search tool. LLM action input. Tokyo weather today. System executes the tool, gets the result. Observation fed back to LLM. Tokyo is 22 degrees C with sunny skies. LLM sees the observation. Next thought. Okay, got the weather, 22 degrees C and sunny. Now I need to recommend clothing for that specific condition. LLM action.sopiogus.han. Recommend clothing. LLM action input. 22 degrees C, sunny weather. System executes the clothing tool. Observation fed back to LLM. Light clothing recommended t-shirt, shorts, sunglasses. LLM sees this observation. Final thought. Perfect, I have the weather and the clothing recommendation. I can now construct the final answer. LLM final answer. Tokyo is 22 degrees and sunny today. I recommend wearing light clothing like a t-shirt, shorts, and sunglasses.
That breakdown makes it crystal clear how it uses the tool's output, the observation, to guide the very next step. It's methodical.
Very methodical. It decomposes the problem and gathers information piece by piece until it's solved.
And implementing this, again, involves frameworks like LangGraph, managing the state, and tool calls.
Exactly. You define your tools as Python functions, often using a decorator like @tool. Importantly, the description you write for the tool, its docstring, is crucial. The LLM uses that description to understand what the tool does and when to use it.
So good documentation helps the AI use the tool correctly.
Absolutely. Then you manage the state, usually in an agent state object. This holds the history of messages, human input, AI thoughts, actions, tool observations, typically in a list under a key like messages. This ensures the LLM always sees the full context.
Got it. And the LLM setup.
You load your LLM model, like ChatOpenAI, making sure to provide it with the available tools. The critical part is the system message or initial prompt. You explicitly tell it, you are a helpful AI assistant. Think step by step. Use tools when needed. Output using the thought action input observation final answer format. This guides its behavior.
Instructing it on the ReAct process itself.
Precisely. Then you set up the graph nodes. One node, often called call model or agent, takes the current state, the message history, and passes it to the LLM. The LLM responds with its thought action output.
And another node for the tools.
Yes, a tool node. If the LLM's output included an action, this node extracts the tool name and input, executes the corresponding Python function, gets the result, and wraps it in a tool message to add back to the state.
And the looping logic. How does it know whether to call a tool or give the final answer?
That's handled by conditional edges. A function, let's call it should continue, looks at the last message in the state. If that message is an AI message containing a tool call, action, it directs the flow to the tool node.
Go run the tool.
Right. But if the last message does not contain a tool call, meaning the LLM likely produced a final answer, it directs the flow to the ND state, terminating the process.
Clever. It dynamically routes based on whether the AI needs more tool interaction.
Exactly. You compile this graph node's edge's entry point and then invoke it with the user's initial message. The system then runs through the loop, printing out or tracing the whole thought action observation sequence till the final answer is reached.
So you can actually see the AI's reasoning process unfold.
That's a major benefit of ReAct. It makes the AI's thought process transparent and actionable. You can see why it made certain decisions or used certain tools. It's crucial for building trust and for debugging when things go wrong. It's not just a black box.
It really exemplifies methodical problem solving by the AI. Breaking things down, using tools, observing results, very powerful. Outro. Wow, what a journey today. Seriously, we went from the absolute simplest AI agents, those pure instinct machines.
The if-thens.
Right, all the way through agents that build mental maps, have goals, optimize, and even learn from experience like that chess bot.
And culminating in these advanced agents using Reflexion and ReAct.
Yeah, agents that can reflect, seek evidence, cite sources, and reason step by step using tools. It's a huge leap from basic automation to something that feels much closer to, well, thinking.
It really is. That ability to not just respond, but to reason, actively seek out information, and self-correct based on evidence or observations. That's a massive step change in AI capabilities. It's moving into adaptive problem solving.
We've really seen how adding just a bit of memory or a clear goal or that sense of utility and especially the power of learning completely transforms what AI can do.
Fundamentally changes the game.
And when you combine those internal capabilities with structured ways to communicate, like using Pydantic schemas and these sophisticated iterative processes like Reflexion and ReAct, you get something incredibly powerful. Hopefully you listening now have a much clearer picture of these building blocks.
Cutting through the hype to the core mechanics.
Exactly. So as we wrap up this deep dive, here's something for you to think about. Given these abilities, learning, reflection, planning, tool use, what really complex problems could you imagine these advanced AI agents tackling next?
Big questions there. Science, medicine, climate.
Maybe. Or even turning it inward, how could we maybe apply some of these principles ourselves? Could adopting a bit of a ReAct approach, consciously thinking through steps, identifying needed info, observing results, or a reflection approach, pausing to evaluate our reasoning, seeking external validation, actually improve our own decision-making?
A fascinating thought. Applying AI principles to human cognition.
Something to ponder. Thank you so much for joining us on this deep dive today.
Thanks for listening.
Keep that curiosity burning, and we'll catch you next time on The Deep Dive.